Okay, Pamela already...
You're also giving the first talk.
Yes, yes. Well, Pamela's already gone over what we're going to be talking about today. So we'll just go straight into the first presentation. Talking about the lunar network, and we're mostly going to be at the vision level with this particular one. And Abraham, feel free to jump in when there are things that can be expanded upon. I'm coming at this from a scientist point of view, and Abraham is coming at it from the enterprise expert point of view. So let's go ahead and move on to the next slide, please. The vision that we're looking at, I really like the way that Russell put it yesterday. We're looking at putting a cloud over the moon where you don't have to bring everything to be capable or viable with you. You don't have to bring your own. You can plug yourself in to the system that is already there. DARPA came up with this idea about fractionated spacecraft, so you can build a capability from multiple components. It was called F6. I like to think of that as a backplane in the sky. So you take your specialized sensor component, the thing that you want to do, you get it up into space and you plug it into your backplane, and you can get comm perhaps, maybe you can get power, maybe you can even get some mass from that as well if you need that. MMA was talking about platforms as well. So the idea is to put that together as a lunar, around the moon as a lunar cloud. And from the enterprise viewpoint, and also from what Courtney was saying yesterday, well, maybe you don't plug right into something at the moon, but maybe you're plugging into something back on the Earth as well. And so that's something very important to think about. Going back to DARPA F6 again, they had a package, the F6 package, that they were talking about flying on board the spacecraft. That, in my mind, and I don't know if it was in DARPA's mind, but in my mind, that was a lot like a network interface card. So following Russell's analog back to the ISA bus-based PC, you know, if you want to connect that to your web or to a modem or anything else like that, you needed a network interface card. Plug that into your PC and then get online. So that's one of the things that we're talking about here. You know, what's your network interface card? And maybe Courtney would say, well, I want a DSN NIC for you to put into your CubeSat. All right, so a bunch of services provided by the cloud. How do you plug yourself into that? And you could have a number of nodes. And one of the things about nodes that Abraham likes to talk about is that the node doesn't have to be one node per spacecraft. If you can have multiple nodes actually on board one particular platform, and then it's all internet out. All right, let's go on to the next slide, please. Okay, shifting focus. There's a big shift that we're undergoing here in the space industry, particularly with regard to science, maybe less so with regard to communications. You know, we're shifting from a mission focus to more of an infrastructure focus. So if you're coming into this with your CubeSat, with your particular mission, with your specialized component that you want to plug into that, you're still sort of at the mission focus, but we want to develop an infrastructure that you can depend upon so that you get more bang for your buck. You don't have to bring your own infrastructure with you. Now currently, what we're looking at here, first, it's sort of a tactical thing. Russell likes to talk about how you're going to have a lot of people going to the moon. They're going to have missions there, primary missions. They reach the end of their missions, and in order to be reliable, they have an extended capability, which may or may not be used. Let's go ahead and make that, repurpose that extra capability and use that to build up the infrastructure. And that'll be the first platforms in that infrastructure. What we really want to do, we want to move to the point where that is your mission, being part of the infrastructure. So that's the strategy. Okay, so moving from this mission focus to a point where each of us is bringing something to the infrastructure that other people can plug into. And a big question is, how do we do that? All right, next slide, please. Again, one thing that hasn't really been talked about, we've heard a lot of great technical discussions and a lot of interesting things that we can do. But there's one thing that kind of concerns me that hasn't been talked about, and that is, how do you control these things? The fundamental way that we control these remote assets, to my mind, is that you have a team on the ground, you have a village on the ground, they're doing the mission planning, they're doing the mission simulations, you're putting together command sequences testing them through all sorts of different contingencies, building up a set of rules, and then you're sending that up to the asset to be executed. All right? And then you have a certain level of autonomy in there in case something goes wrong, so that you can have a fail-safe on that. The problem I have is that right now we're in sort of a sweet spot where if we put something out there and we get some data back from it, we're okay. But when you get a little more sophisticated and you want to start commanding it to do things, you want it to be a little bit reconfigurable. If you want it to be slewing to make, say, a cross-link with some sort of high-gain antenna on your spacecraft, you're starting to think, okay, now I have to start commanding the thing. So are we going, for every CubeSat that wants to do that, are we going to have a team on the ground putting together that simulation capability, putting together those command sequences? You know, it takes like, what, 100, 200 people to do that planning for the Mars rover. We can't do that for a lunar rover. We can't do that for 1,000 CubeSats. Okay, so what we have to do, we have to figure out ways to control our CubeSats with a lot less resources. You have to be able to control many, a multi-platform mission with the same resources that, it takes to do a single mission, and then perhaps even less as well. All right, next slide, please. All right, so there is currently a lot of autonomy. That's one of the things that gets me interested in going for these systems. It's been an important part of deep space missions for a long period of time, because it has to be. You want to have some reliability that your asset is going to be able to take care of itself and contact you if something goes wrong. Also that you have some degree of confidence that when you tell it to do something, it's going to do that. So people have been working on autonomy so that the spacecraft can take care of itself until it can contact you. And so time of flight differences, latencies in that sort of communication have all been important parts of that equation. Lights out operations, it sort of deals with costs. So the autonomy doesn't necessarily have to be all in the spacecraft. You can actually have some of that back on the Earth as well. So that, if you look at the system as a whole, what are the costs for actually getting the mission done? Now, one thing that we've seen recently with a few problems with aviation, there's a caveat that I have down here. I don't know if you can read it, but sometimes it's dangerous to mix autonomy and people, because if you have a 99% solution, sometimes that 1% that gives you a problem because people aren't ready for when they're needed to handle that 1%. So generally, you like to aim for 100% autonomous solution is ready for you, and then you have ways to take over when you need to. All right, next slide, please. This is just a slide that goes back to 1984. People have been looking at autonomy for quite some time. And you can even argue that some of the early systems like the BeepSats, they're autonomous, they're working on their own, but they don't have much reconfigurability. And as we get more sophisticated with our missions, we want to have a lot more reconfigurability. And for that sort of thing, these considerations, those safety considerations become more important. One thing that I always like to talk about is that most of the systems that you talk about when you're sending up commands, it's essentially all rule-driven. When you start talking about autonomy, you're starting to allow the system to start to make choices on its own. And there's a natural trade-off between the rules you give a system and the choices that you allow that system to take on. And the big problem, the big thing that you need to develop these days is how do you get it to make the right choices? How do you build confidence that the system is going to make the right choice when it really needs to? And so there's a balance between the rules and the choices that you put a system in, that you allow a system to take on. Next slide, please. Before the service-oriented economy, there's a period of time where you had behaviors put together as agents, acting as proxies for people, where you would give a software agent a little task and it would go off and do it for you. And that was a way of dividing up the different tasks or behaviors that a system might have, and then programming them, and then trying to analyze them, see how stable the system was, see how effective it was at achieving the mission goals. And over at Goddard Space Flight Center, came up with an idea of progressive autonomy where you could actually work on those behaviors. You define those agents down on the ground, and then you could move them into the ground segment, the operational segment, where you could actually have them start to take a little bit of responsibility over the spacecraft, and then eventually you could migrate those behaviors to the remote platform itself. Now, as time went on, we went from agent-based technologies to the service-based architectures. And some of these ideas actually went on and became what we now know as the cloud and the service-oriented architectures. But here, the point here is that dividing up the tasks into different behaviors and lining them up as agents, there are a number of ways that you can analyze the system's effectiveness, performance, and capabilities in terms of these units here called agents. Next slide, please. So what we're trying to do in moving from a mission-oriented focus to an infrastructure-oriented focus, here's another cartoon. The idea is that you can open up different ground segment options, democratize the capabilities, as Russell likes to talk about, maybe even add some cross-links so that when your system arrives on station, it can take advantage of the capabilities being provided by those who have gone before you, so that, again, you can build up the capital outlay in the infrastructure over time rather than bringing your own each time. All right, next one. So I talked about this a little bit before, the Lunar Network. It's the lunar cloud providing different kinds of services, mass, energy, information, a plug-and-play backplane in the sky. Now, if you know anything about backplanes, they can provide energy, they provide information, they have a protocol for interacting with them, they have things to handle, they have protocols for handling bus contention, who gets to use this communication channel, all that you're going to have for a lunar network. And you have a lot of interesting technical things to go into that. A lot of it's going to have to be autonomous and automated. A lot of that autonomy and automation is built into the hardware and the network infrastructure that we take for granted, even in this room. I mean, there's the wireless microphones. Imagine if we had to be sending command sequences to the wireless microphones so that they're at the right attitude to talk to the communications tower stack back there. Now, we don't have to worry about that so much because we're pretty close. We can deal with low amounts of energy. However, these are things that have to be revisited, and I believe that the automation, making the spacecraft autonomous, providing hopefully commercial solutions or even open source solutions to the CubeSat community so that they will be able to plug themselves into that backplane in the sky. All right, next slide, please. Okay. So in going from say a sort of a pipelined architecture over to a networked architecture, you're going to have to add a number of things. You're going to have to worry about routing, fault tolerance, different sorts of strategies for communication. And again, I think you're going to have to do this in an automated fashion. Next slide, please. One of the things, what is it? The moon is a harsh mistress. Yes, space is very unforgiving, and it shows you where your problems are. So whatever you do, it has to be resilient, and it has to be resilient not only because of the things that go wrong because of the space environment itself, but it also has to be able to deal with things that you do wrong. Software causes a lot of trouble. The information aspect of these systems are difficult and do cause a lot of trouble. So you have to come into this sort of network system with resilience being a question that's on your mind right from the beginning. And the way that we do that with our conventional sort of spacecraft systems is that we narrow the problem as much as we can. We focus on getting rid of the degrees of freedom to the largest extent possible. And you see that again and again in the sort of trade-offs and the engineering that we do. However, as soon as you go to multi-platform systems, as soon as you say, okay, you're going to be able to depend on resources that are going to be there when you get there, that opens up degrees of freedom. It opens up the choices available to the system. And that is something that we need to address as a community. It's something that we need to address, and it's a big problem. So one of the things that happens when you look at these systems, they talk about the sort of rules. That's one way of looking at limiting system freedom, then opening up the choices. If you have a lot of rules, if you've limited the choices, that tends to make your system more brittle. However, on the other hand, if you have a system that is dominated by choices, well, you have a different set of errors that come in. You tend to over-select. Perhaps you choose the wrong situation. And so there's actually a technical and quantitative way to balance off the rules that you apply to a system and the options that you leave open to it. Okay, next slide, please. All right, so again, controlling everything is expensive and adds risk. Removing choice removes flexibility and activity. And one of the things that's had me going in research for about the past decade and a half is how do you add choice back into these systems? And then how do you do it on appropriate timescales? Because you have reactive timescales because things happen quickly and you may not be close enough to help out the spacecraft. You have adaptive timescales where you can sort of nudge the system to where you want it to be. And then evolutionary timescales where you're making big changes to the systems as you go over time. For example, you're adding new spacecraft, new capabilities. Next slide, please. Now, when I was at NASA Goddard Space Flight Center in about the year 2000, we were looking at a different kind of swarm, a different kind of cloud, and it was the Prospecting Asteroid mission. It became a design reference mission for going out to the asteroids and surveying as many of them as you could. So we were aiming at 1,000 asteroids. Some people knocked that down to 100. Doesn't really matter. But the point is that we had specialist spacecraft, and for example, some just took data, others did compute, others were the long-range, long-haul communications. And then these guys were supposed to work together in teams. All right, so we had some of the things that we're actually looking at doing with the lunar networks at the moon. Now, we needed to study the system resilience, and we came up with a few ideas for how you actually analyze one of these systems to hopefully, if you're doing this beforehand, that you can figure out how to build it in a resilient manner. But also, you can take the same methods and go to an existing system and analyze how it's going to perform and what its resilience is going to be. It's called neural because it's a many-to-many connections, okay, and we can keep track of each of those. Keep track of each of those connections. There's a network of rules and choices built into the system, so you can take a particular component, figure out what its behaviors are, and then see what sort of rules and choices are available to that part of the system. And you can analyze an entire system this way in a hierarchical manner. Next slide, please. The function that we developed in this sort of analysis methodology, it's called the neural basis function. And all that is, that's a particular behavior that the system is supposed to have. So there's a component in the system, an imager, it's supposed to take pictures under these sorts of conditions. You'd use that to define this neural basis function. And it's a neural basis, the neural basis function, it's somewhat in an analogy to basis functions in mathematical physics, where you can take this behavior, take that behavior, add them together, and you get another behavior. So you can actually build up different behaviors by adding these different functions together. So there's a certain set of rules and structure to these basis functions. You can analyze your system according to this, look at the different rules and options that are available to the system, and by following the methodology, you know what the interconnections are, at least to an approximation. And so we can take a look, we can turn the crank on this analysis, and we can start to understand the resilience of the system and how the different components interact. So on to the next slide. So the lunar networks, it's a backplane in the sky, providing different services. There's a lot of work to be done in understanding how you provide these different services in a cost-effective way. One of the things we usually like to talk about, the point solutions are inherently brittle. So we want to open that up, okay, make it possible for make it possible for you to build systems where you don't bring your entire infrastructure with you, and make it possible so that we could actually build that network interface card so that you could take your particular PC with its own specialty and plug that into the system that's already there. And one of the interesting things is that we're going to have to figure out how this is going to behave, how you're going to exchange these services. Some of these are going to be commercial, so who's going to actually be doing that bidding for that one particular service over another? Some of that's going to have to be automated. Some of it is going to have to be, some of it might even be done at the moon itself. Okay, that's one of the architectural considerations that we should be looking at. And I would say that we can use these methods that we developed at Goddard to actually answer some of those questions in a quantitative manner. All right, so with that, open it up to questions, and perhaps Abraham might like to share some things as well. Go ahead.
Thank you. I come from the enterprise world, and working with Pamela Clark and Michael Riley is an honor to get into the space of space. And it took a while to kind of appreciate what all things go up there. While I'm very comfortable dealing with the terrestrial networks for commercial enterprise. So now we've got the little hooks here and there, and I think there's a huge potential, like revisit of the internet explosion is likely to happen in the space world, and we have the witness here. So please join us and continue to support what we're trying to do, the Lunar Network. Okay? Yes. We are continuing with the question and answer session. Please go ahead.
I have a question. So could you comment about the implications for this approach starting in the design phase, the importance of using this approach in the design phase as well as in the operational activities?
Can I respond to that? The initial stages, we are not going to be much different from the traditional approach, such as the CubeSat and dedicated way of handling ground networks. One of the ways that we start to kind of integrate these ground stations will kind of move around with ability to relocate, if you will, the operations center, for example. Okay, and on the space world, there are several add-ons that Mike and I have discussed, and I let you throw some light there.
The question during the design phase for these sorts of considerations, nobody's going to build their system to the lunar network unless they know what's going to be there. Okay, so it's not quite a chicken and an egg problem. But what you're going to have to build in some sort of baseline capability, or go along with some friends so that you have brought along your own carrier or something in order to get your data back. Now, once you start to get some capability of the lunar network, that can actually be an additional benefit on top of your own baseline mission. But I think when you're first starting out, you're going to be wanting to go for that baseline unless you can start to get that guarantee that you're going to have some infrastructure capability there.
But in terms of coming up with a solution for what would be a reasonable approach, potentially an optimal approach for how you should develop the infrastructure, where you should put your network nodes.
If you can get a community together and show that there's a market, then you can start to get people to actually invest in the infrastructure. And then if you have a lot of others who are actually using that infrastructure, then you have something that you can work with.
Russell? Needs a mic.
Yes, Eric?
Yeah, let me ask a quick question.
Go ahead.
If I was wondering if you can use examples from the terrestrial network kind of evolution of how, for example, the internet managed to evolve from, when I was first using it, it was 300 baud, and now it's, 30 megabits. But somehow with the different layers, there were certain things that stayed the same, but as hardware refreshed, because we're going to end up with spacecraft that have been launched years ago, and we're going to have ones that are brand new, and even Planet Labs, as soon as they launch their spacecraft, they upload a new set of software because just in the weeks waiting for launch, their software has changed.
Right, and oftentimes people will ship a spacecraft to Mars without the software even being finished. So knowing that they have another year or two to work on it. Abraham, would you like to say something about the development of the Internet?
I wasn't quite ready for that.
Got to pay attention.
So back to the Internet, when it kind of only DARPANET was heard of, and then as it became available to commercial speeds, like he said, starting with 300 baud, text-only, green screen, to where we are now, like close to 25 years has kind of brought us into megabits and gigabits and simple things which could be done with analog devices. Even went deliberately into the digital because they're able to constantly upgrade versions and have all sorts of unnecessary features, if you will. Okay. Now, how does that relate to this? These are very good learning steps that if you hang on only IBM writes the rules of the game, we will be stuck there. When it was democratized that the entire network, regardless of the geographical boundaries, except with several exceptions, that we were kind of free to do quite a bit as long as the connectivity was maintained. Now, one of the first focus will be around how do we have shareable communication paths, multi-paths to reach the same sources and multiple destinations on the ground, and so on. So, in real simple words, extend the Internet that your cell phone is going to work right up there, and from the cell phone there you will be able to browse and do things like here. That would be a simple comparison, but the complexity of doing that is tremendous, and that's the kind of a networking that we are addressing.